Okay, I'm going to start class today with a quiz. I'm just kidding. I'm just kidding. No, I'm going to start today with something I normally don't cover in this class, just because it's not really necessary, but I think it's an interesting result. So you all have heard of this, I'm sure. How many of you have taken physics? Yeah? Okay, well, you may have heard of this, the law of conservation of energy. Yes? You've heard of that before? So there's a couple other things you may have seen before. Let's see how much physics you can remember. Have you ever seen this before? 1/2 mass times v squared. What's that? Kinetic energy, right? So these are some physics terms that you may be familiar with. Kinetic energy. And what's the other type of energy? Potential. Potential and kinetic energy. So let's say you have an object that you move from point A, to point B, however that is that you move it, and let's say under some sort of you're moving it against some field, could be gravity, could be magnetic, whatever it is. Then the law of conservation of energy says pretty much that the kinetic energy of the object at A plus the potential energy of the object at A should equal the kinetic energy of the object at B plus the potential energy of the object at B. Does that look somewhat familiar? Physics? Okay. In other words, energy is conserved as you move one point to the other. So I'm try, if I can, to prove this. Okay, prove the law of conservation of energy. All right? All right, so let's do this. Let's start with this. Let's say that we have some field F. All right, and let's not even care about what the components are, if it's two-dimensional or three-dimensional. We just have some field. Might be gravity, might be magnetic, like I said. And let's say that we have some path R of t is a path, right? This is some field. And let's say t goes between little a and little b. And the picture we have is that our object moves from point A to point B, capital A and capital B. Then let's consider, first of all, the work done in moving it from capital A to capital B. All right, so work, we know by definition, is the line integral over the path C, which in this case, this is C, right? So it's going, I should label this. This is C also, and we're going that direction. So it should be that F dot dr, right? Okay, now, this field here, okay, if we're moving something, we did this last class, that field, we can figure out what the field is if we're moving an object that has a mass, right? We can figure out what force is by mass times acceleration, right? We did that last class. So let's keep in mind here that the force acting on the object as it moves along the path, r of t, is equal to mass times the acceleration, right? And what is the definition of acceleration? According to our path, it will be mass times what? Second derivative of r of t, right? Like this? You with me? Okay, so if we come back to this, this should be the integral. Now I'm going to be able to say from A to B now because everything's going to be in terms of little t. First of all, our field is this, mass, times r double prime of t. And then I'm going to dot that with what's dr? Derivative of the path, which is r prime of t. R prime of t dt. Do y'all agree with that? Okay, now one little side note, everyone. What if I were to take r prime, ask you to dot it with itself, and then take the derivative of this with respect to t. Now, don't necessarily ask why I'm doing this yet. What's the algebra that we would do here? What's the derivative with respect to t of this dot product? Do you remember how we do that? It's just like the product rule. That's all it is. It's derivative of this dotted with that plus the derivative of this dotted with that. Okay, so let's see what that would be. So derivative of that, r double prime of t, dotted with r prime of t, right? Plus, same thing, right? Yeah. R double prime of t, dotted with r prime of t. So that would be equal to 2 of the r double prime of t dotted with r prime t. Y'all agree with me? So what I would like to do is I'd like to take this expression right here. You see that that's right here? Do y'all see that we have that expression right there? Yes? I'd like to take that expression and turn it into this. But this is 2, right? So to go back to here, right? To make it match with that, I need to divide this by 2. So I'm going to divide that by 2, which really makes this times a half. Is that right? And I'll just put that half out here. Sorry. Okay, so this now becomes, watch what I'm going to do. I'm going to pull mass out, and I'm going to pull the half out. So half mass integral from A to B of what? R double prime. Well, no, we're changing this back into this, right? Yeah. So this is going to be r prime of t dotted with itself. So what happens when there's another property here. What's the definition of this?
Magnitude squared.
Magnitude squared. So if you take a vector and dot it with itself, so if you do u dot u, you get magnitude of u squared. Does that look familiar? Yes? Okay, so now this becomes this magnitude squared dt. Wait, I'm forgetting something. I forgot the derivative out front. Derivative with respect to t, right? This is not this. It's the derivative of this, right? Yeah. Okay. Let me rewrite that. I don't like the way I squeezed that in there. So this is d dt of the magnitude of r prime of t squared dt. And do you see what happens now? What is the...
You're integrating the derivative?
Yeah, I'm integrating with respect to t, the derivative with respect to t. So they're going to offset each other, and all that's going to come out is this piece, right? So what we have now, I guess I don't need this anymore. What we have now is that this should be equal to 1/2 mass, and then we're going to have the magnitude of r prime of t, right? And then evaluated at the 2 endpoints, right?
What is it?
Squared. The squared. What's squared? Yeah, it's right there. Get your eyes checked, Milton, please. Thank you. I'm not picking on you anymore. I told my wife about that. She told me to leave you alone. Okay, so this, let's plug in b, and we get this, right, squared, and then minus 1/2 mass this at A squared, right? And we know that the first derivative of the position function is velocity, right? So this is half of the mass times the velocity at B squared minus half the mass times the velocity at A squared. So that tells us that and this we said was what? When we started class, if you came in a little late, we said this is the kinetic energy, right? This is kinetic energy at what, B? Sorry, at time B, right? Which corresponds to, this is R of B right here, and this is R of A right here, right? So this is the kinetic energy at, let me change this, at the point capital B, and this is the kinetic energy at the point A, right? Okay, that's the first thing. So I mean, I guess we could write it, let's put it down like this. We'll just summarize it here. Work is equal to the kinetic energy at B minus the kinetic energy at A. Does that make sense to write it that way? Kinetic energy at B minus kinetic energy at A. That is what the work is. All right? Now, moving on. Suppose that your vector field is conservative. What does that mean? So now we're kind of clearing our minds a little bit here and we're starting over. Suppose we have a conservative vector field. That means that that f is the gradient of some scalar function, right? And in physics, the negative of the scalar function is the potential what do they call it here? Potential energy? Yeah, potential energy. At XYZ. So in physics, we define potential energy to be the negative of this scalar function f, that when you take its gradient, you get the field. All right? You okay with that? This is more of a definition than it is anything else. So in physics, they'll call this, potential energy of X, Y, Z. That's what they call it, P of that. So instead of, for us, that's negative F, all right? Now, what's the work done here? So work will be equal to integral over C of F dot dr again, right? But this time, what's F for us? This is the gradient of little f. So this is the line integral. Let's see, let's go to A and B. A and B of the gradient of little f, right? Dotted with dr. So what's dr? Well, we don't really even need it, actually. Let's see if someone can figure this out. What is this? Very important result from last class. If you're trying to find a line integral, let's move this back to C. If you're trying to find a line integral over some curve C, and you have a conservative vector field, right, that this is the gradient of some scalar function, then the fundamental theorem of line integrals says all we have to do, yes?
Evaluate f at a and b.
At the two endpoints, right?
Yeah.
Evaluate, this says, fundamental theorem of line integral says, all I have to do then is evaluate the scalar function at the endpoint of the curve minus the scalar function at the other endpoint, the starting point, right? Which for us, if f is the potential, right? Right? Isn't f the potential? Then we have, hold on, let me make sure it's going to work. K, B, hold on. This should be negative what? In terms of potential energy, what is this? Negative, what did we say little f was? In physics, negative little f is the potential energy at a point, right? So if I'm giving you a positive f, then that's the negative potential energy at what point? At B. And then this is going to be negative again, but negative is going to be plus the potential energy at A. So this is like the work in terms of potential energy, and that's the work in terms of kinetic energy. And the work has to be equal, right? So if we set these equal to one another, what do we get? If I set that work equal to this work, I get kinetic energy at B minus kinetic energy at A should be equal to negative potential energy at B plus potential energy at A. And if I move the potential over there, this potential over there, and this kinetic over here, I get what I think I started with, right? That make sense? So that's what I started this whole thing with. If you've seen this in physics, that the kinetic energy at the end point plus the potential energy at the end point must be equal to this kinetic and potential at the beginning. This is your law of conservation of energy. But what did it require for us to be able to say this is true? That our vector field be conservative, which actually, that's where it gets the name from. Conservation of energy requires a certain type of vector field. What type? Well, let's call it conservative, okay? Because it conserves the energy. That make sense? So it's a kind of a cool result. The main things, I guess, the big things in it was you needed the line, fundamental theorem of line integrals, which means that our vector field had to be conservative, but that's kind of where it got its name. So it's kind of weird the way the language is there. But all right, so that's it. I just wanted to show that to you all. Let's move on. All right, Green's theorem, right? Said we were going to start that today. So Green's theorem connects the line integral around a simple closed curve to the double integral over the region bounded by the curve. And I want to remind everyone of something here, that the work integral was equal to this integral that those were equal if f is equal to some vector field PQ. So this is just like if you take this, this is just different notation for this. So these mean the same thing. If you were to take whatever the vector field f is, PQ, and then dot it with dr, then this is the relationship between the line integral written in vector form and then the line integral written in the first way we saw it, which was with respect to x and y. So we need this to be able to move on. All right, let me proceed. So let's take a look at Green's theorem. Somehow we're going to turn line integrals into double integrals. That's what this is all about. So first we need some definitions here. A positive orientation. Okay, so this is a definition. Positive orientation of a simple closed curve C refers to counterclockwise traversal of the curve. So right now we're only looking at a two-dimensional picture. That's all we're going to do. And then in a later section we'll go to three-dimensional. So imagine we have a curve sitting on a flat sheet of paper. Then if we go counterclockwise around it, then this is called positive orientation. It's a closed curve, right? C is a closed curve. And that means if it's closed and simple, meaning it doesn't have any holes or any weird things going on, or it's not looping upon itself, then this is a simple closed curve, and that means it must enclose a region D. So D is the region inside, C is the curve, positive orientation. Got it? So here's the theorem. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. So the picture we just saw. If P and Q have partial derivatives on the open region that contains D, in other words, it makes sense for us to take derivatives within that domain inside that curve, then the line integral over C, the closed curve, that was what we were talking about last class, that circle means closed curve, of P dx plus Q dy, this is basically work, okay, is equal to the double integral over D of the partial of Q with respect to x minus the partial P with respect to y dA. Now, I'm not going to prove this theorem, all right? We're just going to use it. But this is a pretty awesome theorem. And this is what I was saying about the symbol. If we want to go positive orientation, we just put a circle. But if for some reason later we want to go the other direction, clockwise, we'll put, do y'all see that little arrow on there that shows the clockwise? So if there's no arrow, it's understood it's counterclockwise. If there's an arrow, it shows the clockwise direction. I have seen people put that arrow there for positive orientation. It's not wrong to put the arrow that way. Okay, but if you leave it out, it's understood to be, did I say clockwise? I meant counterclockwise. All right, so I think the best way to see how this theorem works is to just do an example. So we have this line integral over C of y dx minus x dy, and C is the unit circle centered at the origin. So what we're trying to do is go along this unit circle, right? This is our C. Trying to go along this unit circle and evaluate this line integral. So Green's theorem says, let's go back and take a look at the theorem. Maybe we should write down the theorem over here, just so we have it. Line integral closed curve C of P dx, right, plus, be careful there, plus Q dy is equal to the double integral over D of the partial of Q with respect to x minus the partial of P with respect to y with respect to area. All right. So for this particular problem, do you all see that we have a line integral over closed curve C of y dx. Now we don't have plus, do we? We have minus. So I'm going to say plus negative x dy. So that's the same thing, right? That's the same as that over there. I have a plus here now. So can you tell me right now what P is and what Q is? P is y, and Q is negative x. So we have to check some things. You know, is C a closed curve? Well, C is the unit circle centered at the origin, right? That's a closed curve, right? We're going to do positive orientation, which means when we draw the curve, we want to draw it this way, right? Do you see that it encloses some region D, right? That's D in there. So we can convert this into a double integral. What would that double integral be? Double integral over D, right, of this. What's the partial of Q with respect to x? negative 1 plus, minus the partial of p with respect to y, which is 1. And I'm doing this with respect to area. Now that's just negative 2 in there, isn't it? So this is just negative 2, pull that out, double integral over d of what? 1 dA. Right? And what is this integral? This is the area of d, isn't it? And we can do that without even doing any computation. Because this is d, right? And that has a radius of 1. So the area of that's pi r squared. So the area of that's just pi, isn't it? Understand? So this is just negative 2 pi. Just make sure you understand. This right here is the area of D. I told you that was important, right? Back in the day, I said, remember that formula? Okay, and the area of that is pi. Pi r squared, but r is 1, so it doesn't matter. Okay, that was pretty fast, wasn't it? Okay, let's compare that. Let's compare that. Just what would we have had to have done had we not had this, right? Had we not had Green's theorem? We would have had to have find the parametric equations for C. So C would be, let's see, our parametrics would be x is cosine t, right? Y is sine t. And then we would need dx and dy, right? So we would have dx is negative sine t dt, and then dy would be cosine t dt, right? It's actually not too bad, but let's just do it. Let's see what would this become. Integral from where to where? 0 to 2 pi. I didn't put that here. I felt like it was kind of understood. Was that understood? That t would have to go from 0 to 2 pi? Okay, so we're going to go from 0 to 2 pi. Then we're going to do y dx. So y is sine t times dx, which is negative sine t, dt, right? Plus the integral from 0 to 2 pi. So now I'm doing this one. Negative x, which would be negative cosine t, times dy, which is cosine t dt. And I could put that all into one integral, couldn't I? Yeah, I could put that all into one integral. So if I put that all into one integral and then factor out a negative, right? What would I get? Negative comes out, integral 0 to 2 pi. If I factor negative out of here, it'll be sine squared t plus cosine squared t, which is just 1 dt. And now the antiderivative of that is just t, and you evaluate 0 to 2 pi. 2 pi goes in, we get negative 2 pi and 0, so we get the same answer, right? A little more work though, right? A little more work. The name of the symbol?
Yeah.
I don't know. I don't know if it has a name. I mean, like this is your integral, right? Integral symbol. And like that with this, I'm not quite sure that has like its own name. Because all this is doing is telling you that you're integrating over a closed curve. Maybe it does, but I've never heard of it.
Okay.
Yeah. I mean, like that would be a double integral, right? So I don't think there's a name for that. I don't know. You can look it up. Tell me. I don't think there is, though. Okay. So that one, I was able to show Green's theorem worked real fast. And then the other way we could do, we could do if we needed to. But what about that one? Okay. So let's just take a step back and appreciate what it would take to do this. We would have to figure out the parametric for this, right? Which we could do. This is a circle of radius 3. So we could do like 3 cosine t, 3 sine t. So x would be 3 cosine t, y would be 3 sine t. But then when we came in here, replace this would be like 3 times 3 sine t minus e to the sine of what? Cosine, 3 cosine t. And then dx would be the derivative of 3 cosine, so negative sine. And we would have to integrate that. And I think that would be pretty bad. And if that wasn't bad, this one's going to be really bad, okay? Do y'all see how bad this would be if I replaced that right there with 3 sine t? And how do you, yeah, okay? So this integral looks like it would be extremely tough, yeah? Okay, now what we can do is we can use Green's theorem. So what is p in this problem for us? Yep. So this is p. And we have the plus sign, right? So we can just go straight here. This is q. And we have that this was a closed curve that enclosed a region D, right? Right? We needed that it be closed. 3 is the radius on that thing. So we should be able to convert this over to a double integral. So this should equal the double integral over D of the partial of q with respect to x. Q with respect to x. I'm going off that formula over there. 7. Minus the partial of p with respect to y. 3 dA, right? Which is just 4. Pull it out. Double integral over d of 1 dA, which is just the area of that enclosed region again. Doesn't always work out that way, okay? It's because I'm working on a circle, this is pretty nice. But this right here requires really no computation. It's just pi r squared, right? So for us that would be 9 pi, right? Because the radius of our circle is 3. So times 4, so this is 36 pi. Look at that. I mean, like, we could, if we had a chance right now to sit back and start this problem over knowing what we know, we could probably crank that out in under 2 minutes, right? Maybe under 30 seconds, depending on how comfortable you are with it, right? I mean, that is just a tremendous shortcut on that compared to what we would have had to have done the other way. I'm like tempted to plug that into the computer to see what it would do. Like if I replaced all these with 3. No, let's not do it. Let's not do it. Okay, make sense? All right. So I think if I were you, if I'm sitting there looking at a take-home test or a final exam, and you're asked to evaluate a line integral, and you have a closed curve, I would be thinking, can I do this with Green's theorem, right? Because, I mean, think about it. Think about some of the curves that we've looked at in the past. Like, I don't know. I mean, if you have something, even something like closed curve like that. Like if you don't have Green's theorem, you're going to have to break this down into 3 separate curves, 3 separate line integrals. 4 separate line integrals. Find parametric representations for each one. And it can be really a mess. But if it's enclosing a solid, then Green's theorem should be in play. All right. So we can see sometimes computing the line integral over a closed curve is easier when we use Green's theorem and convert the problem to a double integral. But there's other cases where we can actually convert a double integral over to a line integral. I'm sorry, Milton. I was kidding.
No, I haven't done this.
I was kidding.
I'm sorry, so I just can't do this anymore.
I was kidding. I understand.
It's not you, it's me.
Have a good one, Milton.
You too.
All right, so we can actually use Green's theorem backwards, all right? But it's not as straightforward. We have to consider something here. If you look at this formula, I'm recording, yes, my microphone is. If you consider this formula, like here they give us any P, any Q, and we're in business, right? But from here back, it looks weird that our double integral would have to look a certain way in order for us to go backwards, right? Does that kind of make sense? That these would have to be like partials in order for us to go this way. And like we had just a second ago, we had 4, didn't we? 7 minus, what was it? 7 minus 3 or whatever, yeah, right? And we got that 4. So if you just had the 4 sitting here, like how would you know where that came from to get back to these two? Does that make sense? So it's not as straightforward, but we can be clever. So watch. So remember with double integrals that this, we already know this, the area of D is the double integral over 1. Or the double integral of 1 over d dA. So we know that. Now, if we look at this formula right here, we ask ourselves, when could this be 1? Right? So we're looking at a very special case right now. Could we ever take this double integral and turn it back into a line integral? Could we? All right? So what would it take for us to be able to take that double integral and turn it into a line integral? We would have to have that this right here is that piece right there, right? Yeah. Okay, so then we ask ourselves, in what scenarios could we ever get these partials to be equal, the difference of these partials to be equal to 1? So here's one scenario. If we were to define that p function as 0 and q is x, then that would be 1, wouldn't it? If I say take the partial of q with respect to x, you would give me 1, right? Then minus partial of p with respect to y, you would give me 0. And that'd be 1, right? So if the p is the 0 function, the q is the x function, then this double integral right here would transform into this. Do y'all see where this is coming from? It's this formula with p replaced with 0, it's gone, and then q replaced with x. And so you get that. That makes sense? Now, that's not the only way you could do it. You could also do it another way. You could let p be negative y and q be 0 this time. So if p is negative y and q is 0, if q is 0, this goes, if q is 0, then this would be 0. And then if p is negative y, when you take the partial with respect to y, you get negative 1, then subtract and you get plus, right? So that's another way. And then the third way we won't check, but you could just let each of them be p is negative 1/2 y, and then the other one is 1/2 x respectively. And if you do those partials, you'll come up with the same thing. So all three of these, this one, and this one, would all give you the area of D. All right? All right, so how are we going to use that? I love this example. Find the area of a circle, radius r. So we've already done this, haven't we? We've proven where the formula for a circle comes from. But I'd like to use Green's theorem to do it. So right now, if I take a circle of radius r, right, then the way we would want to do this is to define this to be d and do the double integral over d of 1 dA, right? That would be the area of that. Agreed? So we could go through and we could try and do this. How would you do that double integral? If I forced you to do a double integral, how would you do it?
You have to do like the dr d theta.
Dr d theta. Yes, okay, I think you're talking about polar coordinates, right? You would do polar coordinates for this. You would take this region right here, and you would convert to polar. So you would say, okay, like my theta is going to go between 0 and 2 pi, and my r is going to go between where? Maybe I should make that, let's make that capital R. Yeah, let's make that capital R. My r is going to go between 0 and capital R, and then you'd set up your double integral, right? And this wouldn't be bad, okay? We could do this, and it's not like we're saving ourselves a lot by converting this to a line integral, but I want to show you that you can get the same result. Okay, so this, I want to convert over to a line integral over a closed curve of C, and we had 3 choices, didn't we? 3 choices of what we could do here. Let me go back. Let's do the first one, where P was 0 right? And q was x, right? And that line integral becomes x dy, right? So I'm going to say p is 0 and q is x. We're doing the line integral over c. Now c is the curve going around, right? Around this, right? Like that. So that's your c. So we need to have some parametric representation of c, which I think we're all okay with, right? C would be what? X is, yeah, but our radius is capital R.
R cosine?
Yeah, capital R cosine t, and our y would be capital R sine t, right? T is obviously going to be between 0 and 2 pi. And we'll need the derivatives of these also, won't we? So dx is negative capital R sine t dt, and then dy is r cosine t dt. If you don't like the way I'm writing these, you could put the dt underneath the dx or the dt under the dy. It's all the same. All right, so let's rewrite this line integral then, right? This double integral of 1, right? Double integral over d of 1 dA. According to Green's theorem, if we let p and q be those things, will turn out to be this every single time. And that for us, with that parametric representation, should be a line integral, an integral from 0 to 2 pi of x, which for us is r cosine t, and then times y, or sorry, dy, which is r cosine t again, dt. Got that? So this is your dy, this is your x, and now capital R is a constant, right?
Yeah.
So let's pull that out. So if we pull capital R out, capital R squared, integral 0 to 2 pi, and we'll have cosine squared in there, right? Cosine squared of t, which we'll use the power reducing formula on, which turns into 1/2, what is it?
1/2 plus 1/2 cosine.
Plus cosine of 2t dt. So sometimes we write the 1/2 here and here. I'm going to just put it here and pull it out. So we have 1/2 capital R squared, integral 0 to 2 pi of 1 plus cosine of 2t dt. And now we should be able to integrate those individually. I would argue that polar coordinates we would have been done already, okay? But this is just showing you how the theorem can be used, all right? So now, antiderivative, so 1/2 r squared. The antiderivative of that is going to be t, and then plus 1/2 of sine 2t. And then we're evaluating that from 0 to 2 pi. Y'all see what happens with that sine stuff? Like when I let 2 pi go in here, I get 2 pi, right? And then here, sine of 4 pi is 0. And then what happens when I plug in 0 here and here? 0, 0, so it's gone, right? So the only thing I'm going to have is the 2 pi right there, right? And then we put the 2 pi next to that, you get 1/2 r squared, and then times 2 pi. And these cancel, so you get pi r squared. It all works. So, moral of the story is that there are ways to take certain double integrals and convert them over to line integrals. Most of the time, it's easier to go from a line integral to a double integral, but the theorem can be used both ways. Now, here's one. Hold on. Find the area of the figure below, an epicycloid. Find the area of this thing. Ooh. So check this out. This is our region D, right? We're trying to find the area of D. So we want to find the double integral over D of 1 dA, right? That would be a very difficult problem to do because this is not, you cannot do this with polar coordinates. This is not a circle, it's not a polar region. These are the parametric equations. They've already been given to you, all right? So if you start plugging that in, you know, like start plugging in values of t between 0 and 2 pi into here, it's going to start to draw this thing. So do you see the challenge it would be to try and come up with the area of this? But we have the freedom now to convert it to a line integral. So do you want to just go after do the same thing? You want to do p is 0, q is x, or you want to do one of the other two? I don't care.
Let's do
The second one, what was the second one? P is negative y, and q is 0. So let's try that one instead. So this will be negative y, and this one is 0. So we're just trying the second method to see what happens. So that means this double integral becomes a line integral over the closed curve C of negative y dx, right? Okay? Now the great news is y is already defined, right? Y is already defined. We know what y is. What else do we need to know? Dx, right? Dx is the derivative of this. And we know the restrictions on t. So we have everything we need, don't we? Do you all follow me or no? Yeah. Okay. So that should become integral going from where to where? 0 to pi. And then negative y. So what's negative y for us? Negative 5 sine t plus sine 5t. Okay. And then we're going to take that and we're going to multiply that. I'm going to erase this. We're going to multiply that by dx. Now dx I didn't write down on the board, but we can just do it up here. Derivative of this with respect to t would give us what? Negative 5 sine t. And then plus derivative, not anti. So we still have, no, it's plus. It's plus 5 sine of 5t dt. Agree? Dx, negative y. Now, this is not that great of an integral, but I mean, I think things do get, I don't know, do they multiply out and become good or no? Let's just FOIL this out. So here to here, 25 sine squared t. And then here to here, we have minus 25 sine t. Oh yeah, okay. Negative 25 sine t sine 5t. And then the middle one, oh, is it the same thing?
No, it's minus 5.
Minus 5, okay, yeah. So minus 30. It's 5 sine 5t. No. Sine t sine 5t. So, and then our last one is plus 5 sine squared 5t dt. Yeah, and that middle one will become negative 30, right? So let me just put it together here. I realize this is not like the best integral to be looking at, but tell me what your other options are, right? I mean, I don't think anyone's going to be able to do that with a double integral. So we got that, and then minus 30 sine t sine 5t. And last one is plus 5 sine squared 5t dt. Is that doable? Is that a doable integral for you? How would you do this first one? Power reduce, right? So this would become like half of parentheses 1 minus sine, cosine, sorry, minus cosine 2t, right? And then this one, you could do the same thing, right? But what about that middle one? How could we do sine t sine 5t? That's one that you don't see too much. Go ahead.
I was going to say U substitution.
U sub, yeah. That one actually won't go easily with any technique that we have from Cal 2. What it's going to take is a pre-cal formula. We have formulas in pre-cal that take products to sums. Are you looking at your formula sheets there? No. No? Who has their formula? Okay, look at your formula sheet. I know you have yours, right? This is your product to sum formulas. This would be from pre-cal. I don't see them here. I don't see them. Let's just look it up.
Oh, these ones. This one's like cosine u plus b cos u cos b minus sine u sine.
Yes.
That family of formulas.
Yeah, there's a whole family of let me see. Oh, this is,
Seems to are-
I'm just trying to pull some random stuff here up off the web. Here we go. See if that one. No. There they are. There we go. This is not the best version. I'm sure you could find them somewhere else. But right there. Sine of A times sine of B is equal to half cosine A minus B minus cosine A plus B. So when you use this formula, you'll be able to take that and split it into two separate trig functions, both in cosine. And then you could just do those individually and it'll come out pretty clean. Make sense? I'm not going to go through it. Just want to show you, like now it's doable. All right, so we proceed. It's pretty cool though. I mean, we get the area of that, right? I mean, those are all doable integrals, so.
You also do
So-
like 0 to pi over 2 and then just multiply the answer by 4.
0 to pi over 2? Yeah, I'm not sure if that would spare us anything in terms of the integration, right? But you would also have to verify that between 0 and pi over 2 that it is drawing this, right? Oh wait, no, hold on. We need a closed curve. I think that's dangerous. I think that's dangerous. Yeah. I mean, do you agree that if you could find the antiderivatives of this, like plugging in pi over 2 and 2 pi, it's not going to make that big of a difference?
So, sir, when you were first explaining how it needed to be a closed curve, you also said that it had to be smooth in other aspects. So, but it can still have things like a cusp or an edge and be smooth. What
Well,
would be-
there's a lot of things that, wait, smooth as in,
I thought that was one of the words that.
yes. Let me go back to it. Piecewise smooth. So that means that there are pieces that are smooth. So you go like that first piece is smooth. Yes, it's bad at that point, but there's another piece that's smooth, and another piece that's smooth, another piece that's smooth. So piecewise, it is smooth. Overall, there's 4 places where it's not because you have those little things. That's a good call, yes. If it didn't say piecewise, if it had to be smooth, then we would have a problem. I was talking to, I have an online Cal 3 student who came in for some help today, and she's really been asking me some really good questions. And we were talking about how a lot of these theorems, they have little subtleties in there that we really don't get too deep into in this class. Like, you know, okay, so what if it wasn't piecewise smooth, right? Well, we're not going to do a problem like that, you know. So there's a lot of conditions that have to be met that we just kind of gloss over. Piecewise smooth is one of those ones where I'm not going to give you something that wouldn't be, right? Because then the theorem wouldn't apply. So, but all these theorems, every single word in here is important for the theorem to hold. If you take one thing out, the theorem's not going to hold anymore. All right, let's keep going. So imagine you're sitting there taking the final exam and you're asked to compute this. I'm asking you to compute the work, right? The work done by that field where C is this triangle. So I'm not sure where you start with this. Maybe you look at that and you initially say, hey, maybe it's conservative, right? This is kind of, let me see if I can't blow your mind a little bit. See if I can't blow your mind a little bit. What should, if I have a closed curve, and the vector field that I'm integrating over is conservative, what should the line integral be? So if I have a curve, starts here, goes around, and comes back here, and I ask for the line integral over that closed curve of C of f dot dr, then what's the answer if this is a conservative vector field?
F of R of...
Okay, so it's the little scalar function at the end point minus a little scalar function at the starting point. But if it's a closed curve, then starting and ending is the same, which means your answer should be 0. Do you all agree with that? That's a huge thing here. If you have a conservative vector field, if it's conservative, right? If f is conservative and you have a closed path, right? Then the fundamental theorem of line integrals says subtract the two endpoints, right? And so we should get 0. But what was the test we had to see if a two-dimensional vector field, to see if it was conservative? What was the test that we had? Partial of partial of p with respect to x had to be equal to the partial of q with respect to y, right? Look at Green's theorem. Partial of p with respect to y has, if it's equal to partial of q with respect to x, these are the same two quantities, aren't they? And so when you subtract them, what do you get? 0. So the double integral should give you 0, shouldn't it? Which matches up with the line integral. I don't know if that makes sense, what I just said, but we just said that a line integral over a closed loop, right, on a conservative vector field should be 0. But if we use Green's theorem, right, we should also get 0. But when you go to use Green's theorem, you do this part, you're going to get 0 here, because it's a conservative vector field. These two are going to be equal and they go away. That's just an observation. It has nothing to do with this problem, okay? All right, I'm trying to think, like, if I were you sitting here doing this problem, maybe the first thing you would do is see if it's a conservative vector field. I don't know. Because if it was conservative, then you would know that endpoint minus endpoint, you're there, right? So maybe you check it's conservative. I don't know. I'm going to start by drawing the C. So my path starts out 0, 0, goes to the point 2, 6, then it goes to the point 2, 0, and then it goes back to the origin.